All right. So now we're working on reflection, and we're going to have a little more complicated version of reflection than if you had me for pre-algebra. First off, you guys get the idea of reflection, but I do want to show you some examples just to make sure you guys get the idea. This is in Budapest, Hungary. I lived in Budapest, Hungary for a year. This is their parliament building. And the city is cut in half by a river, the Danube River. And what's really cool, the river can be very still and it could look almost like a glass. And so you get these awesome pictures of reflection. And so what we're going to have here is where the water meets the ground has this line. And this line we're going to call the axis of symmetry. Now, axis is just an important math word for line, the axis of symmetry. But we're going to have that line move all over the place. So we're going to talk about different ways that line can move around. But you guys get the idea of reflection. So like you can see like this little like window thing here. It's the same distance from the axis of symmetry in the reflection as it is in the normal part. And it's on a straight line, right? It doesn't like waver around or anything. So it just like reflects straight over. Here's another picture. Same thing. You guys get the idea, right? So it's like this little green part of this like dome type thing. It's in a line and it's the same distance from the axis of symmetry. So those are some examples of reflection. But what we're going to be doing will be, like I said, a little bit more complicated than just that. So one thing we need to know is the axis of symmetry. And really, the axis of symmetry, axis is, again, that word just means an important line or a line to take note of. And so the axis of symmetry, it's the line where the image mirrors. And in this, we're going to have some important lines that we'll talk about, and then other ways, like other lines that will be on there. So first off, they could say an example of the axis of symmetry could be the x-axis. And so when something reflects across the x-axis, it reflects up and down. So actually, let's think about this. Let's draw it this way. Here's your graph. This is the x-axis. And this is the y-axis. So for it to reflect across the x-axis is like these pictures of the river, where see how the x-axis is a left and right facing line, like the edge of the river here. And so the reflection goes up and down. It's kind of confusing because x normally you think about things going left and right, but to reflect across it makes it going up and down because the line's going left and right. So that's kind of like the river. There's other ways that we can make it reflect up and down like the river. And this is kind of confusing, and we can add more to this. They could give you an axis of symmetry like this. Y equals 3 could be the axis of symmetry. So imagine that you have your graph, and do you guys remember graphing the equation y equals 3? You go up 3 to the y-axis. And the way that we're going to draw that out is you're going to draw a dashed line for your axis of symmetry. And then you would reflect it up and down across that axis of symmetry. So it's kind of confusing because if it says the x-axis, it goes up and down. But then if it says y equals 3 or whatever, y equals -1, it goes up and down. The other important line to make it move left and right is the y-axis. So the y-axis makes it move left and right. Oh, you don't need a calculator for this. Don't need it. With the y-axis, an example of the y-axis instead of a river is like your face. Your face should have an axis of symmetry that goes up and down. And so it should go left and right. We'll take a small side note here. You know, you might remember me saying this from pre-algebra, but you know, there's dorky people out there that are such dorks. They put numbers to absolutely everything. And so there were these like math/science people that wanted to somehow quantitate, like give a number to what people thought was attractive. So what they did is they got like thousands of images of people's faces, just their face, and had people of all sorts of different ages and, you know, origins and races and all these different things, just anyone they could get. And then they would rate the face on how attractive they thought the face was of a scale of 0 to 10. And what they found was the most attractive faces were the ones that were the most symmetrical. So it didn't matter like did you have an almond shaped eye or a round shaped eye? Did you have big nostrils or little nostrils? None of that stuff really mattered across like what they found was the most symmetrical faces. So not big or little, just if it was symmetrical, that's what made a face look attractive. It actually makes sense. You don't need to take notes on this, but right? Just imagine you had like one eye that was shaped like this, like, okay, that's fine. We got an eye, but then the other eye was like this, right? It's like suddenly like already looking weird. And then like you had a nose that like had like whatever normal size nostril, and then one that was like really big, right? Like they're already not an attractive person, right? So you get the idea there, like, so, and like the smile's all crooked, you wouldn't think of that as attractive. Again, it's not like the actual shape of each one of the things, it's just how symmetrical it is. So, that didn't really have to do with the lesson, but when that new student that comes in for the fall that makes you feel funny and you see them in your English class and you don't know what to say, I got a line for you. Your face looks extremely symmetrical. That's right. It'll work, I promise. All right, you guys get the idea. So if you reflect it across the y-axis, then it goes left and right like your face. Other examples of lines that go left and right would be like this. X equals -1. X equals -1, you'd go there to the -1. And then again, it would reflect left and right. So what's weird with this though, again, I want to point this out because this is where students do get confused. The y-axis goes left and right like your face, but X equals whatever goes left and right as well. That's a confusing thing. Now, we are not going to do this, but they could have they could have another axis of symmetry. Don't put this in your notes, but they could give you like a crazy linear equation like y equals 1/2 x plus 1. And then you would go through and graph out y equals 1/2 x plus 1 and reflect it. We're not going to do those, but that could be a thing that's done. Really, what's going to happen is you're going to graph things and name coordinates. So let's get an actual example of what's going to happen. They could tell you to like graph and they'll give you a point, like graph point A, and you're going to put A at 2, -3. So you're going to get your graph. You're going to go to the right 2 and down 3, and you're going to put a dot, and you're going to label it A. And then they're going to say reflect that, and then they're going to give you a line. So like, let's reflect it across x equals -2. So then we're going to go and make the axis of symmetry x equals -2 and put a dashed line for x equals -2. And now this reflection, is it like the river or like your face? Right? It goes left and right like your face. So we're going to count how many spots away is A from the axis of symmetry. 1, 2, 3, 4. And so then we'll move it 4 more. 1, 2, 3, 4. We'll put the dot. And now this is the image of A. And then we should be able to say its location. -6, -3. And that whole thing would be actually, this would be the answer. But with those, you're going to have to like sit there and graph it out. They could have some weird ones as well. Like I know on there, they have one where the axis of symmetry is like x equals 0.5. So it's like in between the two lines. The number, any fraction they have is going to stay with a 1/2. If they give you, I'm not going to assign ones. I don't even think they have them. That would be crazier than 1/2. Right. So you should be able to figure them out with like something like that. All right. That is it for our notes.